Okay, we continue talk about elliptic curves. Last time we talked about elliptic curves. An elliptic curve looks like this. The standard form is y square equals some cubic question of x. So that is a typical elliptic curve function. And both a and b, they are parameters. According to different parameters, your elliptic curve can be one piece or two pieces. Okay, so that's what we talked about last time. So what we were talking about last time was that both a and b, they are actually real numbers. They're real numbers. And the determinant is this. The determinant of the cubic equation is 4a cube plus 27b squared. And if this is not 0, then we have a non-degenerate elliptic curve, which is useful. If the determinant is 0, then we have a problem. This type of elliptic curve cannot be used. Okay? So as we talked about last time, as we mentioned last time, we can define an operation called point addition. Okay. First, let me rephrase that the elements of the group is consists of all points on the curve plus an imaginary point called the point at infinity. And adding 2 points is like this. Okay, it can be defined this way. Give me 2 points, P and Q. First, we draw a line intersecting PQ. And then this line intersects another point, intersects a third point on the curve. And what's counterintuitive is that we actually do the mirror point of that one. Okay? And this mirror point is defined as the point that we apply the operation to P and Q. Okay, since this operation does not depend on the order of P and Q, it is commutative. So all group laws, including the the closure, okay, and identity inverse commutativity, they can be proved very easily. The only one that is difficult to prove is the associativity. That is why when we mentioned the group law of elliptic curves, we actually refer to the associativity, which is really difficult to prove. In fact, the designer actually took the idea from algebraic geometry, and then actually this group was very famous in algebraic geometry. If you guys have any chance to learn this type of this subject, you will realize that it is actually a very common group. But the designer of the elliptic curve, they applied this group to the discrete log based problems, and they got really good results. That is why it's fantastic. Okay, and then since this group is really difficult to understand, there are less and less people who are familiar with it, and therefore there are less less attacks, because basically nobody is familiar with this group. If it's defined in this counterintuitive way. So we mentioned about the adding 2 points. That's a definition. And if in some cases when these 2 points to be added actually lies on a vertical line, then it does not intersect any point on the curve. In this case, we simply define their sum to be the point at infinity. Okay. It's actually a really good way of doing that, and because we can actually define the inverse for each point in this. So the point of, for any point, its inverse can be defined as the mirror point with respect to the x-axis. Okay, so that's adding points. Now we're going to talk about adding p to p. Suppose we have a point p and then we want to add p to itself. In that case, we cannot follow this definition. We cannot use this definition because this definition only holds when p and q are two distinct points. However, if p is equal to q, obviously we cannot draw a line intersecting intersecting one point. Okay, so in this case, what we can actually think this way. Suppose we fix p and then we let q approach to p. So q is a variable point. So as q approaches to p, this intersecting line converges to the tangent line of p. Okay, the tangent line of p. So in the limit case, when q is actually overlapping with p, okay, in that case, it's actually a tangent line. So it's the tangent line. We can use this tangent line to define p plus p, and we have a special technical term for that. We call this the doubling a point. Okay. So doubling a point, how to formally define point doubling is that first we draw a line which is tangent to the point P, okay, and then this line actually intersects another point, and then we do the mirror point according to the horizontal axis, and this mirror point can be defined as the doubling of the point P. Okay, so this follows naturally when we have already defined point addition. Okay. So that's the idea. Now let's look at a special case. Let's see, we have a p here. Okay. First we do a doubling. Okay, p plus p. So we draw a tangent line. Okay. And this tangent line does not intersect any point on the curve. In this case, we define the doubling of point p as the point at infinity. So in other words, the doubling p plus p, we can denote it by 2p. Okay, we denote this by 2p. So 2p is actually defined as the point at infinity. Okay, and then we can do 2p plus p according to the addition formula. So 2p plus p, since 2p is 0, okay, I mean the point at infinity, which is the identity. So when the identity is added to p, okay, 2p plus p, which is actually 3p, so 3p is equal to p. And then 4p, that goes back to point doubling, because p plus p is the point at infinity. So we have this type of alternating points. If we consider p, 2p, 3p, 4p, 5p, we'll realize that if we have an even number, k, okay, then kp is actually equal to the point at infinity. And then if it's an odd number, the odd number, then it is equal to p. So it's like if we keep adding point, okay, 1p, 2p, 3p, 4p, then we just switch back and forth between p and the point at infinity. Okay, so p and then 2p, 3p, 4p, like this. 5p, 6p is equal to the point at infinity. Okay, so we have a special case. Actually, this is a bad choice for a generator. So obviously this is not a good generator, because on elliptic curves, what we're going to do is we actually choose a point, and preferably it can be a generator P. So let's see if we choose a point G here, and then we draw 2G. What is 2G? Then we draw a tangent line like this, and it intersects a point here, and then we do the mirror point. This will be 2G, and then 3G is 2G plus G. We draw another line, and then we, according to the formula, we get another point. So we have G, 2G, 3G, 4G, and hopefully it can cover the whole curve. Okay. Obviously, it's a very difficult question whether or how to choose a point G so that it's a generator. Now, this problem is much more complicated than the group ZP star. The reason is we are really, really unfamiliar with this elliptic curve group, okay? Because it's not numbers. Nobody is familiar with this, and there are very limited mathematical tools we can apply to this type of thing, because the whole group was constructed in an abstract manner. That is why it's kind of difficult, and that's actually a good thing, because there are less attackers. The attackers are not familiar either. Okay, so that's actually a good thing. But it's difficult to choose a generator, right? And let me tell you guys what happens right now. How people uses the elliptic curve group. Let me give you a short answer. There's no way to know which one is the generator, which point is the generator. There's no way to know. We just pick one element, pick one point arbitrarily on a curve, and then just hopefully it will be a generator. Obviously, you don't want to choose this one, okay? Because it switches back and forth between the point at infinity and this point itself. So this is a really bad point, okay? It only covers 2 points. The orbit of this point, if you use it as a base, then it's a really bad choice. And there's virtually no method to keep track of how many points an arbitrary point can cover. Okay, so actually, there's only one way to do that. That's computer simulation. So that is why later I will show you guys about suggested curves and their related points, kind of stuff. Okay, there's no way to know that. The Americans, the NIST, they actually asked RSA people, Certicom, to do simulations, and then they found some good curves, and then we just use them. Okay, there's no way to know how good they are. Okay. Now, the elliptic curves we introduced so far, they are the elliptic curves over real numbers. Okay. Obviously, we have a problem because it is not practical. We cannot represent real numbers using finite memory. That's the main problem. So in other words, real numbers are out of question. There's no way you can use those in a crypto system. Okay. If we use real numbers, we have to sacrifice something, because there's no way to use limited memory to represent these real numbers. We can only truncate those numbers. For example, we sacrifice some precision. Okay, so we use approximate numbers. Well, if you can tolerate the precision, then real numbers can be useful. For example, like in many areas of engineering, communications, all kinds of area, real numbers are very practical because we don't need to use the exact numbers, right? We just take measurements, and then every measurement has a precision. So as long as you can sacrifice some precision, then it is okay. It is usable and it's convenient. It's practical. However, in a crypto system, on the other hand, it's not this case. Okay, if it's anything related to not just cryptography, anything related to coding. Okay, let's see, error correcting code. If you want to encode a number, encode some data, and then you have to decode, right? You have to convert back. So as long as you need to recover some data back to your original data, then you cannot use real numbers, because even the slightest precision error or slightest error will make the whole system unusable. Okay, let's say we just pick a point, okay, and then we pick a point G, and then we do 2G, right? Let's say 2G is here, and then we do 3G, 4G. If we sacrifice a little bit of error, okay, then if it's G, then we do 2G, so 2G will drift a little bit, so the error will become a little larger, and then 3G, this error will expand, the error will grow. So very soon that the amount of error will exceed the actual data, and the whole system is junk. Okay, so you simply cannot use real numbers at all. So if we cannot use real numbers, what should we do? There's only one solution. Okay, we consider the elliptic curves over finite fields. Okay, so this will be a big jump. As we mentioned earlier, like we talk about the AES, we introduce finite fields, GF at 2 to the power of 8, okay, GF to 56. So finite fields, we can do all 4 operations. Okay, in that case, there's no error, right? We use the precise number, but you have to make some sacrifice. So the sacrifice, what are the sacrifices we make? If it's a real number, if it's an elliptic curve over real numbers, then we can actually draw the curve. If it's an elliptic curve over a finite field, let's see, the elliptic curve may still look like this. Okay, we have x cubed and we have y squared, ax plus b. But in this case, both a and b, they are elements in a finite field. Okay, so x, y, a, b, they're all elements in a finite field. Well, we can perform all operations. We can also even solve equations like this. Okay, give me a and then give me x, we solve an equation. That also works in a finite field. But the thing is, you really can't draw a curve. So your curve looks like this. They're just individual points. Let's take a look at this curve, this so-called curve. We have a y square, so y square is okay, so let's use this to represent y. Okay, and then the field, we consider a curve over GF 61, which is a prime field, because 61 is a prime number. So we can use 0 to 60 to represent the elements. Okay, so it's prime. And then what happens is here we can still have this number -1. So -1 is actually 60, because 60 and -1, they're considered the same thing, because everything is mod 61. Okay, so this still makes sense, but we don't have a curve. We only have these individual points, and then these points, they are symmetric as well. So we have a positive y, then we have a negative y. Even though positive and negative in GF61, they really don't, I mean, positive and negative, they are just two individual points, okay? It's difficult to represent that. I mean, the sign of a number, you have to sacrifice this idea. There's no sign of number. There's no positive number. There's no negative number. Everything is mod 61. So this is a special curve. And anyway, we still have this type of symmetry. If we have a positive number, then we have a negative number here. Even though you can actually regard this as a positive, and then this is negative. Okay, and then those individual points, they are not continuous. So the concept of this type of smooth curve are gone. There's no curve anymore. They're individual points. So what problems do we have? We also have a problem. For example, like, let's take a look at the problem. So adding 2 points. If you add 2 points, can you do that? Okay, you have 2 points and then you draw a line. Okay, well, the thing is, does this line really intersect another point? That's one question. And then you do the mirror point. The mirror is okay. The mirroring is okay. But how can you be sure that you can actually this intersecting line will intersect, and this line will intersect a third point? How are you sure of that? Well, this can be dealt with when we talk about the formula of these elliptic curves. So this is okay. But we do have another problem. The bigger problem is the point doubling. You gotta do a tangent line. Well, whoops. The concept of tangent line disappears. You only have these individual points. What's the idea of tangent line? Okay, so that's a problem. But this problem can be dealt with. Let's take a look at the algebraic approach. So algebraic approach, how to do that? First, let's consider now 2 points, okay, P and Q. And then these points are on a curve. The curve is this. Okay, let's just choose a curve. The generic curve y squared is equal to x cubed plus ax plus b. So we consider a curve. We have 2 parameters, a and b. Okay, and then what we do here. So for this moment, let's assume that these a and b, x, y, they are in the real number. They are real numbers. Let's temporarily assume that. Okay, and then we're given 2 points P and Q. Okay, well, for real numbers, we can actually calculate P plus Q using a formula. So first we consider we define another curve, another parameter, which is the slope of the point, the line passing through P and Q. So this is the slope. This is understandable because this is the difference in the y-axis divided by the difference in the x on the x-axis. Okay, so this is the slope. There's no big deal. And then using these parameters and using the formula, using these parameters, we can actually calculate a formula. And then we have a representation of R. So R is given by x3, y3, and then we have a formula here. x3 is lambda squared minus x1 minus x2, and then y3 is here. So that's point addition. Point doubling also works. Okay, so suppose we have a p here, and then we can calculate the formula for 2p. Okay, giving the slope is this. Here the slope is calculated using elementary calculus. Okay, actually I encourage you guys to just calculate it yourself. These formulas are not difficult. They're easy to calculate. Okay, you only need all you need is high school conic analytic geometry with a little bit of calculus. Anybody can calculate it, I'm sure. Okay, so we can derive the formulas for point addition and point doubling for elliptic curves over real numbers. That is no problem. Okay, so that's algebraic approach. So for algebraic approach, we can actually define, okay, define the addition, define this operation as the set of formulae, the set of formulas. And we can define the point doubling as these sets of formulas. That's another, this is an alternative way to do that. Now, before we jump to the idea of elliptic curves over finite field, how to deal with that problem, let me briefly take an excursion to the characteristic of a field. Okay, so suppose we have a field, but suppose we have a field, we have a special characteristic in algebra. Okay, this number represents the behavior of the field. That's you add. Okay, you add the multiplicative identity. You keep adding that. If there is a time, okay, that if you add those, okay, it will equal to 0, then the smallest possible number to make this happen is called the characteristic of a ring, of a field. Okay. So in short, let's take this field for example, GF61. So 61 is a prime number. We add 1, so 1 plus 1 is 2, okay? And then 1 plus 1 plus 1 is 3. We keep going until we hit 61. So 61 mod 61 is 0. Okay? So 61 itself is the characteristic of this field, GF61, okay? And in the field, we just introduced in AES. Maybe we can take a look. Okay. AES, I think it's lecture 4. Okay, let's take a look. The GF256, GF256. If you guys remember how this field is constructed. Okay, we consider binary polynomials. Okay, polynomials ring with binary coefficients, and then we consider this irreducible polynomial. Okay, and then the field numbers. What are these field numbers? Those field numbers, they are actually polynomials over, okay, if you guys remember, those are polynomials mod this mx. Okay, so anyway, let's take the additive identity 1. Okay, if we keep adding 1 plus 1 is actually 0. So in this case, the characteristics of this GF256 is actually 2. So as we can see that for general finite field GFP, we know that any element, the number of elements in a finite field must be the power of a prime. So for this type of fields, actually, okay, yeah, for some reason it's behaving weird. Okay, anyway, for this type of field, GFP to the power of n, the characteristic is p. Okay, so that's finite field. Okay, back to the elliptic curve. Now, so for any field, actually, we can define the characteristic of a field. If a field is finite, then we always have a characteristic. Okay, because if it's finite, then we know that if you keep adding these elements, there's no way you can create you can introduce new elements, because when you have elements, you keep adding one to it. Okay, you're going to create an infinite set. However, if the field itself is finite, then there must be a there must be a collision. I should say, let me use another words. There must be a repetition, because if you're working in a finite set and then you keep adding these numbers, the act of adding those numbers will introduce different numbers if no repetition happens. But we know that there's no way you can avoid, there's no way you can keep introducing new numbers without repetition, right? So at some point, repetition must happen. In that case, it's very easy to prove that if a repetition happens, then that repetition will be 0. Okay, so that's the characteristic of a field. And this idea can be extended to the characteristics of a ring. Okay, and if a ring contains the additive identity, then that is okay. That's exactly the same definition. However, if you guys remember, when we define the idea of rings, rings really don't need to have multiplicative identity. So in that case, we have a different definition. But that's not important. I put it here just for the sake of completeness. If you guys are interested, you guys can take a look. It doesn't matter. Okay. So anyway, let's just focus on the characteristic of a field. Okay, we don't need to use the characteristic of a ring. Okay, and sometimes if such number does not exist, a very easy example is the field of real numbers. You add 1 to 1, you get 2, and then you add 1 to 1 to 1, you get 3. So we have 1, 2, 3, 4, and then it goes to infinity. Since the field of real numbers is an infinite set, it does not violate anything. No repetition needs to happen. Okay, so in that case, nothing is violated, and then it is not necessary to go back to wrap around to 0. In that case, there's no number n such that this will happen. Okay, so if this does not happen, then the characteristic is defined to be 0. So the characteristic of the set of real numbers, a set of complex numbers, a set of rational numbers, okay, those are fields. Their characteristics are all 0. And also, I mean, we can consider the characteristic of a ring. So we can consider the characteristics of a set of integers, which is a commutative ring with identity, and that characteristic is also 0. The characteristic is really important because when we actually go from real numbers to finite fields, it plays an important role. Okay. So anyway, the calculations with real numbers are slow. Yeah, because floating numbers, okay, real numbers, they're slow. And then rounding causes inaccuracy or error. And as I mentioned earlier, if your system can tolerate errors, okay, to some precision, to some accuracy, then you can use real numbers, no problem. However, in some systems like cryptography, so this is the subject we're studying, or some coding subject like error correcting codes, that kind of thing, you cannot use real numbers. They're not practical, because you simply cannot tolerate rounding errors at all. If there's anything that has some error, then you cannot recover. Then the whole thing is junk. Okay? So then we can only use elliptic curve, okay, on finite fields. That's the best approach. That's the only way we can apply those. And then there are two types of fields that we can use. We know that the number of elements in a finite field is some power of a prime number. Okay. However, we won't use GFP to the n in general. We only use two types. Either we use the GFP when p is prime, or we use GF 2 to the m. Okay, so here in this case, okay, we use base 2, okay, 2 to the m. We only use these two finite fields, and I believe that these are the finite fields that are most practical. For this finite field, like our earlier example, we have GF61. Okay, we have a special name for that. This is called a prime field because it's a prime. Okay, the number is a prime number. And then we also have a special name for this. This is called a binary field. Okay, and binary field is also very practical because all computer hardware, everything is binary. We're living in a binary world. Computer scientists are all binary. Okay, so these are two important fields. No other fields will be useful to us, computer scientists. For example, like we'll never use GF, for example, 3 to the power of m. This is not practical. Nobody cares about such field because there's no computer system is ternary. Everything is binary. Nobody cares about that. Okay? So because it's a finite field, there are only a finite number of points that are on the curve. Okay? And that means there is no curve anymore. They are just individual points. No curve. So this is a huge leap. So you guys are actually, use your imagination. I think you can probably you think when we talk about elliptic curves, we think this way. We think there's a curve, but when we actually use them, they're not. Those are not curves. They are just points. That's an elliptic curve group. So that's a huge leap for us. I hope you guys can use your imagination well to understand this subject, because this subject is really a little bit complicated, abstract as well. Okay, so there's no curve anymore. Okay, and it follows immediately that geometric definitions of addition and doubling don't work on these curves. In other words, these concepts does not work anymore. Okay, they are. I introduce these concepts just to help us understand this object. They don't exist anymore. Okay? So geometric, no, they only help us understand. However, algebraic definitions still hold. In other words, we simply define the addition and doubling like this. We can examine whether it makes sense. Okay? Now, these points x1, y1, x2, y2, x3, y3, the x, y, y1, they're not real numbers anymore. For example, they're field elements. Okay, but anyway, we know that field elements, they're abstract, right? Because we have learned AES, and then we know prime fields. Well, but what we can do is we could really do all four operations: addition, subtraction, multiplication, division, square. There's no problem, right? So they actually hold. You can just apply these formulas without any problems at all. Let's say if you write it using a higher level object-oriented language, okay, and then you just initialize your this x y1. If it's a real number, you just initialize it as a floating number. But now we switch to the we simply switch to finite fields, right? Well, let's take C++, for example. It doesn't make any difference because we can use virtual functions, right? So this is we can define those abstract classes. So these are, as long as addition, subtraction, multiplication, division, these member functions still work, we don't care which type they are. They are finite fields, they are real numbers, complex numbers, doesn't matter at all. They still hold. So additions, they're fine. Doubling also hold. Okay. Although we have a little problem. Okay. We do have a little problem. What's the problem? The problem is, in some cases, if you're really unlucky, your characteristic is something weird. Okay. By something weird, I mean actually characteristic too, because we only use these two. We only use these two types of fields: prime field and binary field. So the characteristic of this one is p. The characteristic of this one is 2. So you guys may think, well, what's the difference then? What's the difference? Let me tell you what the differences are. For prime fields, okay, the characteristics p, there's no problem at all. The problem lies in the case where the characteristic is 2. So this is doubling. Well, we have a problem because we have this number 2. So this number 2 is actually 0, because if a field has characteristic 2, that means 2 is equal to 0, like what I've learned in AES. 2 is basically 0. Okay? You can never divide by 0. So if it's in the denominator, then you have a problem. So this set of formula is useless. So the doubling does not work in this case. Well, it does not work in this case. It does not mean it is not practical. We just have to find some patches. Okay, we have to, use other definition, use other ways to kind of get around this problem. Otherwise it won't work. Let me see. Yeah. Otherwise it won't work. Okay. So we have to. This one. Algebraic definition holds. So in order to deal with this problem, we have to introduce other stuff. So we introduce the Weierstrass form. So Weierstrass is a German mathematician who did lots of contribution in some like fundamentals of analysis. He actually systematically studied the elliptic curves as well. So he actually used this form. So we have y squared plus, we have introduced the cross term xy. In our earlier case, we only have y squared and then x cubed, and then linear term, and then constant term. In other words, we only have a4 and a6. Okay. In Weierstrass form, they actually introduce a1, a2, and a3. Okay. If we are not using the binary fields, then we don't need to use this. Okay. If we just use prime fields, then we can simply use a4 and a6. without any problems at all. Okay, now we just need to introduce A1, A2, and A3 to counter the problem of dividing by 0 if you use binary fields. Well, you guys may ask, why do we need to use binary fields? Are there any advantages? Let me tell you guys. Actually, the answer is yes. The reason is, for general purpose elliptic curve crypto systems, general purpose ones, okay, you use prime field. That's the easiest one. However, if you have special hardware, actually it's even better to use binary fields. The reason is, our computer, if it's designed in a way that, I should say our computers are designed in a way that binary operations can be performed extremely fast. And then if we use binary fields, a lot of the operations, all these operations are binary. But the thing is, you just have to avoid some cases. Those cases will slow you down, right? However, if you avoid those cases with special hardware, your system can have better performance. So generally speaking, for general purpose, you use prime field, elliptic curve over prime field. For hardware supported, special hardware elliptic curves, then you use binary field, because you can use special binary operations to speed up your algorithm. Okay, so if you have special hardware to do that, then it's actually even better to use binary field. So in particular, if this is the case, then we need some special treatment. And then fields with any other characteristics, they are not important. So nobody's interested in those. Okay. Now, for any elliptic curves over a field with characteristics not equal to 2 or 3, then we can apply ordinary, our ordinary formula, just like what we did with real numbers. Okay, so exactly the same thing follow. Okay, so the determinant is non-zero. Okay, and then there's no curve anymore. The definitions are purely algebraic. Okay, and then the elements are these xy pairs. Just these x. The only difference is that these x and y's, they are in the prime field. Okay, and we also have a special point at infinity, which is the additive identity. And then those formulas, they're exactly the same. Inverse or mirroring formula. Okay, we have a point P, and then you want to calculate minus P, so you just do the mirroring point. So addition, doubling, they are exactly the same thing. Okay, no problem. However, if we're using elliptic curves over a finite field whose characteristics is equal to 2, then we cannot use a above mentioned method. We have to consider two special types. One of them is called 0J invariant, the other is non-zero J invariant. Okay, so the 0J invariant, we introduce this one, A3. We don't need to have A1 and A2. We don't need to have a square term here, and we don't have to have a cross term. So we have A3, introduce a new variable. And we can also use non-zero J invariant. So we have a cross term, the cross term. And then A2 and A6, okay? So that's non-zero J invariant. As we can see that, what's the difference? Actually, this one is easier, right? This one is easier. 0J invariant, the behavior is better. But as we can see that, you need an extra parameter, A3. Okay, so you have 3 parameters. Okay, for previous ones, we only have two parameters. So two parameters will represent a curve. However, for this case, you need three parameters. Okay, and everything else, the speed, everything else is the same. For non-zero J invariant, you have a cross term. Well, in that case, we don't need to have another term for that, a parameter for that. We can fix that one, and then we just change the A2 and A6. So we only need to handle two parameters. Okay. If you compare these two types, they're roughly identical. It just depends on whether you want to sacrifice a little more for the number of parameters, or you want to sacrifice a little bit of understanding, I would say. Actually, computational wise, there no difference. So for zero J invariant, actually what you do is, it's pretty easy to understand. Let me use this one. So zero J invariant, it's like your elliptic curve has been translated vertically. So it's like your x-axis may be here. Okay, your x-axis is here. So your x-axis does not pass through the middle of your elliptic curve. Your x-axis passes here. So that is called the zero J invariant. So in that case, the mirroring is a little different, because the mirroring is, you do the mirroring with respect to the x-axis instead of the middle of the curve. So it's not just switching sign. You have to add something else. That's it. But just because of that, if you derive a formula for that, that will actually prevent from the existence of this number 2. Okay, which is not possible because 2 is equal to 0, right? So if we use that one, let's see. For zero J invariant, the inverse, the mirroring operation is translated. Okay, translated. Just to make sure that you guys know what translate means. Translate 是平移的意思，平移啊，不是翻译。在数学上的 translation 是平移。平移掉了一个值，它就不会产生那个2了，那你这个 doubling 就没有问题了，其他是一样的。So just because we do this translation, the doubling, if you derive the doubling formula, then it's like this. You guys can try it at home, okay? Just do a translation, and then you can derive the formula for addition and doubling. That's it. So that's about it. Let's just stop here, and we'll continue next time with non-zero J invariant elliptic curves. Okay, so that's it.